This is Nina, and I'll be presenting Lab 5, Faraday's Law. Faraday's Law is a basic law of electromagnetism predicting how a magnetic field will interact with an electric current to produce an electromotive force, or EMF. This is also known as an electromagnetic induction. This is done by relating time-varying magnetic fields to curly or non-straight electric fields. Mathematically, this is seen as a path integral around the closed loop as non-zero. The current driven by the EMF produces a magnetic field which exerts a force on the source of the external magnetic force. In the context of this lab, the source of the external magnetic field is a bar magnet, and the induced current is driven through the tube of an aluminum foil. It was imperative that the aluminum foil was at least a half to 1 inch thick in order to drive the induced current. The objective of the lab was to observe the interaction between the falling magnet and the tube of the aluminum foil. This was done by collecting observational data from the magnet falling through a conductive tube of aluminum foil, modeling the magnet and the tube interaction computationally, and comparing the computational prediction with measured values. The materials required for this lab included a smartphone, bar magnet, roll of aluminum, and a meter stick. The methods for this lab were to first mark the north end of the bar magnet using a magnometer, hold the tube vertically, and drop the magnet through the opening. Record the bar magnet entering and exiting the tube, calculate the time it took for the magnet to fall through the length of the tube, and repeat the process 5 times. The following are the times it took for the magnet to fall through the roll of aluminum foil, with an average time of 1.54 seconds. During my experiment, I unexpectedly experienced little to no resistance against the falling magnet. This could be because of a variety of reasons, such as the size of the bar magnet, the thickness of the foil roll, or the length of the aluminum foil roll. Before I go into the computational model, I'll answer the additional questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity was reduced near 0, the magnet would fall at a relatively faster speed. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If the ring of currents in the model were disrupted by slots or holes, it's possible that the shape of the area in which the current travels across would be altered, thus changing the resulting time-varying magnetic field. So unfortunately, the model moves too quickly to be able to accurately display what is happening, so I'll use this time to display my code and answer the associated questions. The code includes calculations of the magnetic moment of the bar magnet, the magnetic field at position R relative to the bar magnet, the rate of change in the magnetic flux through each ring caused by the falling magnet, the current induced in each ring by the falling magnet by Faraday's law, the force exerted on each current-carrying ring by the falling magnet by the Biot-Savart law, the force exerted on the falling magnet by the whole tube of the current-carrying rings by Newton's third law, the net force on the magnet including gravity, and modeling the motion of the falling magnet. The intensity of the coloring on the tube indicates the magnet of current flowing through each ring. Red and blue indicate the current flowing in opposite directions. Which color corresponds to clockwise current and which counterclockwise? How can you know? Red indicates clockwise current and blue indicates counterclockwise current. You know this because by the model, red points downwards, and if you curl your fingers by the right-hand rule, Red indicates clockwise current and blue indicates counterclockwise current. You know this because by the model, red points downwards, and if you curl your fingers by the right-hand rule, your fingers indicating the current will curl clockwise. What happens to the dynamics of the system when you flip the magnet around? If the magnet were flipped with the south end downwards, you would not experience resistance because the magnetic dipole moment would be in the opposite direction. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? Well, since my experiment did not work as expected, the computational system may be more accurate. The computational system could be improved to include more real-life factors that might change the outcome of the experiment as it did so for me. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? It tells us that the magnetic force is represented as a function of time and increases with time. Thanks for listening, and let me know if you have any questions.